In this video, we are going to continue Lesson 2 of Part 1 inside of Unit 3. This time we're going to take a look at some application problems associated with exponentials and logarithms. There will be many application problems in the Math Excel assignments in the upcoming weeks, and here's one type of exponential problem that lends itself well to the use of logarithms. This first part of the problem I don't think requires it, but as we get a little bit more complicated examples, you'll see how we can use them. So this is the compound interest formula, and it says that the amount of money, A, in an account after T years' time with the amount P invested, principal, and an interest rate of R. Now R has got to be written as a decimal, by the way. So we're not going to record this, 12%, for example, would be written as 0.12. So R is a decimal, which represents the rate of growth. And N is how many times we compute or compound our interest per year. So as a warm-up, let's just look at this particular example. Let's say we've got $50 that's invested at 6% interest compounded monthly, which means that N is equal to 12. And we'd like to know how much money is in the account after a period of 3 years. Well, that's pretty straightforward. A lot of times you'll see this formula written as A of t using function notation. So the amount of money is based on the amount of time we leave the money alone. Because that's the one thing that we have control of a lot of times in these investments. So P times 1 plus R over N to the NT power. Let's suppose for a second that we went to a bank and the bank said, well, you can give us as much money as you want. In this case, it's $50. But we're telling you that the investment is only going to return 6% interest, so 0.06, and we're only going to compound your interest 12 times per year. So essentially, the bank has completed most of this formula for you. The unknown value, of course, is t. Well, in this particular case, we're saying that t is equal to 3, so we're evaluating this function at the value 3. And we need 50 times 1 plus 0.06 divided by 12 to the 12 times 3 power. And I like to show this because, well, this is one more opportunity for us to practice with function notation. This A3 doesn't mean multiplication or anything. This is our way of asking us to find the amount in the account after 3 years. So that's what we're looking for. That's what this end result is. And the right side of this equation, well, this is something that can be calculated. We can actually substitute or place all of that into a graphing calculator like the ones we have in the classroom and let the calculator do all of the work in this case. So I need 50 times 1 plus a fraction. A fraction is created by pressing Control, then divide. And we have 0.06 in the numerator and 12 in the denominator. If I press the right arrow to get outside of the parentheses, I can use my exponent command and write 12 times 3. Now before I press enter on this calculator, I'm just going to quickly double check, does what I have in the calculator seem to match what was written on paper? And I would say yes to that. And as long as I'm confident with what was written on paper, then we can be pretty confident that the solution that's presented to us on the calculator is accurate. So as it turns out, a $50 investment left alone for 3 years turns to $59.83. We'll only keep 2 decimal places after the decimal point since this is a dollar amount problem. Normally I like 4. So there we have it. The amount in the account after 3 years is $59.83. So no need for a logarithm or any special exponential rules here. This was a pretty straightforward example. But this problem was cut off when I copied it. This problem was asking how much principal is needed in order to have $1,000 in the account after 2.5 years when we compound our interest at 6%. Pause the video now and see if you can set up this equation. Here's the setup that I would use. Again, our formula was written this way, without function notation this time. And we knew the ending amount is $1,000. We knew our rate, we knew the number of compounds per year, and we knew the amount of time in years that the investment would be left alone. So all we need to do now is solve for P. Well, here again, this expression is something that can be entered into the calculator, and it's just going to come out to be some number. So if my job is to isolate the value P, then really all that I need to do is to divide by this number on both sides, and then the P value will be isolated. So 1,000 should be divided by 1 plus 0.06 divided by 365 to the 365 times 2.5 power. And here again, this is something that we could enter into our calculator. So I know that I need a large fraction to begin with, so I'll press Control Divide to get started. And 1,000 goes in the numerator, and in the denominator, with or without the parentheses, grouping the whole thing, but we do need parentheses around this initial component. 1 plus the fraction, Control Divide, 0.06 divided by 365. Now notice I moved my cursor just to the outside of the parentheses. I didn't move it to the outside beyond that fraction bar. And now we've got an exponent of 365 times 2.5 in the denominator. Now I'm fairly certain that what I've entered in the calculator matches what I had on paper, so I'm confident that whatever the calculator returns, we should have a good and correct answer. And there we go. 860.72. 860.72. So the principal, the amount that we need to invest, is $860.72, so that after 2.5 years it grows to a total value of $1,000. But here again, we didn't have to use a logarithm or an exponential at all to solve. So what gives? Do we ever use those things? Well, let me just make up an example for you. Let's say that you found an account that was willing to guarantee a 6% rate of return. That's pretty high for bank accounts these days, but let's pretend that a bank is willing to give this to you. And they're going to guarantee a 6% rate of return. And you would like to know how much time is needed in order for your investment to double. Now, it doesn't matter how much money you start with, but let's pretend that you're starting with $1,000 and you would like for your account to grow to $2,000. How much time is necessary in order for that to happen? Well, let's set it up. We'll again use the n value of 365, just like we had in the last example, because we'll compound our interest daily. So our ending amount, 2,000, is equal to 1,000 times 1 plus 0.06 divided by 365 raised to the power of 365 times t. Here's where our newest logarithm rules are really going to pay off for us. The unknown variable is here in an exponent. This is going to be hard to solve without the use of logarithms. Now keep in mind that we have the number 1,000 acting as a coefficient that multiplies by this whole group. And this whole group would be simplified before the multiplication because it contains an exponent. We can't simplify it right now because of that exponent, but I do want to point out that we can strip away this number 1,000 and we can move it to the other side of the equation by dividing both sides by 1,000. And what you'll end up with on the left-hand side is the number 2. Now, do you remember me saying that we're asking how long it takes for our investment to double? Well, it doesn't matter how much money you start with, whether you start it with 1,000 and it turns to 2,000, or if it starts at 10,000 and it ends at 20,000, or if it starts at $1 million and you end at 2 million. The first step is to always divide by your principal, the amount that you start it with, and when you divide both sides of the equation, you're always going to end up with 2 in a problem like this. If you want to know how long it takes for your investment to triple, we'll just change this number to a 3 and so on. So there isn't really a need to identify your A or P value in problems like this. Now I also want to point out that this number inside the parentheses can be simplified to a single value too. That might make our work with the logarithms in just a moment a bit easier. So I'll go to the calculator and we'll type 1 plus 0.06 divided by 365. And we see 1.00016, and that's going to round to 1.0002. Because of the extra decimals, I'm going to go ahead and run this out to the 5th or maybe even the 6th decimal place for accuracy. So we have 2 equals 1.000164 raised to the power of 365t. Now, as we get better with our exponentials, we won't even calculate this mid-step here because we're actually losing some accuracy by changing this to a decimal. We had to round in order to make that happen, so we lost some accuracy. But I have no idea what the t value is going to be here to solve this, and this is written as an exponential right now. We've got a base, an exponent, and an output for the exponential, and I have no idea what t is going to be, and I have no idea how to solve it. But if I rewrite the exponential as a logarithm, I might get somewhere. So let's recall that a logarithm with the same base as the exponential, and we could have written this fraction as the base, and our calculator can handle that. But anyway, the logarithm contains the same base as the exponential, and the output of the exponential, the 2 over here, becomes the input of our logarithm. It becomes the argument of the logarithm, and the result of the logarithm was the input of the exponential. And now we're really close to having an answer. This expression on the left is something that my calculator can evaluate. And in order to isolate t, now we would divide by 365, and we know that t is equal to the logarithm with a base of 1.000164 evaluated at 2, divided by 365, and that is the time necessary to let this investment grow. So we again need a fraction in our calculator. And across the top we need a logarithm, and that's this command right here above the 10x button. There we go, I was able to make that a little bit bigger. So in the numerator, my cursor is active in the numerator, so I'll press Control and then 10 to the x power. This allows me to enter the base of the logarithm, 1.000164. The argument of the logarithm is 2, and we're dividing this whole fraction by 365. Now I don't know if I'm going to get a decimal answer or not, but out of habit, since I know I want a decimal answer in this case, I'll press Control Enter. And now I can see how much time it's going to take for my investment to double. Approximately 11.58 years. 11.58 years. And we'll call it 5804, just for the accuracy that I'm after. So that's the result that we get if we had left our the base of our logarithm as the decimal. Let's see what happens if we write the base of our logarithm as a fraction, as indicated here, with a precise decimal amount. Well, I can repeat the prior calculation. Let me try this again. Sometimes, since I'm using a touchscreen computer, I bump the wrong keys. So if I press the up arrow until this expression is highlighted, I can then tap this Enter button, and it's going to copy that expression down. And everything in that expression worked for me except for the base of the logarithm. Instead of the decimal, I'm going to write the entire fraction, 1 plus 0.06 divided by 365, because that's the value that we had to round earlier. And so if we hadn't rounded that, and in this case we didn't round at all until we got to the final answer here, we'd have an end result of 11.5534. So 11.5534. And if I'm being perfectly honest, I prefer this answer because that tells me that you were able to compute it without rounding before the last step. However, if you do produce this as an answer, I'll know where it came from because this is how we just practiced it in this video. I think that's a good point to stop here. There are 2 additional examples to practice with, but these will come later in the Math Excel sets, so I'll wait until a later video to talk about them. Thanks for watching.